Good evening, ladies and gentlemen. Again, this is a short report back on an excellent day that we have spent in the field with Hayley Korthra. Yesterday, she talked about the quaternary geology of our Overberg region, focusing on the young Bredasdorp aeolianites, talking about the Kelders Caves and other aspects of our fascinating geology. We've just spent a wonderful day in the field with her, mostly at the Kelders, and so Hayley, while it's all fresh in her mind, is going to give us a report back of the rocks and the geology and all the things we saw today.
This morning we went down to the Kelders Cave and we investigated the sort of context in which the cave formed. We stood on the Table Mountain Group sandstone wave cut platform, the old erosional terrace, onto which there's this the deposition of a conglomerate at the base and cemented aeolian dunes or aeolianites above that. This unconformity is quite distinct on the landscape, both at the Kelders Cave and also to the west and to the east of it. And there's a sizable hiatus, of course, represented by that unconformity. So either the conglomerate at the bottom might date back to the time of the De Hoopvlei Formation, which is probably Pliocene in age, maybe about 3 million years or so, or it could be of the Klein-Brack Formation, in which case it's about 400 to 440,000 years in age. Both of those were past high sea levels during times when there were warm interglacials. And just to sort of recap, since about 900,000 years ago in the mid-Pleistocene transition, the current climate system and sea level system as we know it now was set in place. And this basically means that we have these periods of warming or interglacials, which are called by the negative marine isotope stage numbers. So MIS1 is the present. MIS3 was a mild period of warming leading up to the last glacial maximum. Marine isotope stage 5E was the last interglacial, when sea level was about 6 to 8 meters higher than at present. Stage 7, about 200,000 years ago, was quite a warm or quite a mild interglacial, and the sea level maximum heights are still not very well constrained along our coast. They might have been slightly lower than at present. And then marine isotope stage 11 is a very important one on our coast. And we believe that it's a probable analog for what we could expect in future based on the orbital parameters at the moment. So if marine isotope stage 11 is in fact an analog of what we would expect to come, we might be in for a very long and very warm interglacial, which might last up to 40,000 years. And sea level might reach heights of about 11 meters higher than at present. And yeah, just characterized by firstly a small peak in rise, which then dropped and rose into a sort of big and long period of warming. So in our case, the small peak would be represented by the Holocene high stand, which was about 7 to 6,000 years ago, where sea level actually overshot the present elevation and got to about 3 meters above present, stayed there for about 1,000 years and then dropped back down to 0 MSL and has been on the rise again since then. So if these conglomerates, to figure it out, the first thing we could do, of course, is to just measure the precise elevation. And then if they could be marine isotope stage 11, they are within the time period of being able to date them using luminescence dating. And that would be a way to determine it. But either way, there's a sizable hiatus represented by this unconformity, because you've got Table Mountain Group sandstones of the Peninsula Formation, which are approximately 400 million years in age, overlain by conglomerates that are either about 3 million or about 400,000 years in age. These conglomerates, for the most part, form, of course, then the roof of the cave at the Kelders, and they are in turn overlain by cemented aeolianite. Cave formation processes are fairly complex, and we see similar patterns all the way along the Cape South Coast, where most of the neocoastal caves are represented by the Table Mountain Group sandstones or quartzites. And these are normally alternating beds of very thick, hard quartzites with some silty material in between, and also thrust faulted material between, which has been sort of brecciated and sometimes almost powdered. And that was from the assembly of Gondwana. So where you have these preferential planes of weakness, such as siltstone layers or thrust fault zones, these are the places that previous high sea levels have carved into to form these caves and overhangs along the coast. Of course, if you have repeated sort of incision by sea level, you're going to have notches that form in areas that are quite resistant. And then in areas that are less resistant, depending on how far in the penetration goes, there's often processes of cliff collapse. And there's evidence for this all along the Cape South coast, where you have large chunks of Table Mountain Group sandstone at present sea level, which means that there was probably a previous overhanging ceiling, which has subsequently tumbled down. Within these cave systems, if you have Table Mountain Group sandstone overlain by something that's calcium carbonate rich, such as an aeolianite, if the conditions are right and you've got fractures in the cave, often water percolating through and precipitating or dissolving actually the calcium carbonates, it could form speleothem or tufa material, which is a calcium carbonate that leads to the development of either flowstone or sometimes stalagmites and stalactites. And these accumulate, of course, over time, and they are very good barometers of the paleoclimate and the paleo environment at the time in which they formed, because they pick up trace elements with them of the vegetation and the type of rainfall that's falling. So these can be drilled and analyzed, and they can be dated using uranium series dating. The analyses that are typically done on speleothem include isotope analyses on oxygen and carbon to indicate the sort of chemical compositions of the atmosphere and the rainfall at the time through the oxygen, and the types of vegetation through the carbon isotope work. So in that case, it's generally a sort of broad brushstroke of was it C3 or C4 photosynthesizing styles of vegetation, and therefore it can be inferred what sort of grasslands or shrub environments, for example, you might have expected at different times in the record. Along the coast at Kelders, Kirsten Brown has actually drilled and sampled some of the speleothems at the drip Kelders Cave, and this is under analysis at the moment. So yeah, so the dominant features along the coast at the moment around Kelders are this, the cave formation along the unconformity, the overlying conglomerate with the debated age, the thick aeolianites above that, which have been dated to 90 to 92,000 years. And that 90,000 approximately time, it's quite a common time in the record of aeolianites on the Cape South coast. There were various pulses of sedimentation at different times in the Quaternary record, and 90,000 approximately is one of those, when there was obviously either good sediment supply or the correct conditions to cement aeolianite from a dune into a rock. It's often the case that the Cape South coast caves have been totally blocked by dunes for parts of their histories. And in some cases, this is why these fine-grained and very erodible deposits have actually been preserved at all. So generally speaking, caves along the Cape South coast or anywhere on the South African coast, if they are more than about 6 or 8 meters above sea level, then they're more promising locations to have older records, because the implication is that people occupying the caves may have been occupying them for more than, let's say, for example, like the case at Pinnacle Point, for 170,000 years. But in a lot of cases, those records that predated the last interglacial, or 125,000 years, were sort of charred out of the cave by high sea levels during the last interglacial. So a lot of the records on the Cape South coast start at about 125,000 and go up into the youngest stratigraphy. But in fact, it doesn't necessarily mean that people only occupied those sites from 125,000. It could be just that whatever came before has subsequently been eroded out, and therefore you almost reset the clock of deposition. In a lot of times you can investigate the sort of the cliff face around the caves or the overhangs or the shelters, And you can look for evidence of bits of cementation from past aeolianites that would have blocked up the entrances and have subsequently been removed, either by high sea levels eroding them off, or sometimes by seismicity, which might have removed the block of the entrance to the cave. Most quaternary rocks in the South African rock record are dominated by either cemented beach deposits or aeolianites. And generally speaking, these are either ancient dune rocks or ancient beach rocks. But beach rock as a term is actually something quite specific. It refers to approximately the swash zone of a beach environment. So not all cemented beach deposits are actually beach rocks. If you had to cut a profile through a typical coastal zone, underneath the breakers, you've got the upper shore face, which is quite a high energy environment. And in the rock record, you often see like cobbles and pebbles and sort of clasts that indicate that high energy system. That grades into the swash zone, which is the intertidal area where the waves sort of wash in and out, often dominated by shell hash and planar bedding. Moving up onto the main part of the beach, that's generally the foreshore, which is slightly finer grained than the swash zone. So the energy sort of decreases or dissipates from the shore face towards the dunes, and the grain size tracks that habit. By the time you get to the back beach and the dune, the sediments are quite fine grained, generally better sorted, and dunes are generally laid down and show facets, which are at approximately the angle of repose of sediment accumulation, so maybe 15 to 30 degrees dip in these facet beds. So when you change sea level, well, in any sedimentary environment, you change water level, for instance, things that are adjacent to each other in the modern environment become stacked on top of each other. So you can look out for these contacts and these changes in the sediment facies, and you can tell whether it was a rising or a falling sea level according to what kind of environment is stacked how. So often on the Cape South Coast, we don't have strictly beach rocks, but we've got cemented beach deposits. And we're normally looking for a contact between the upper shore face and the foreshore or the swash area, which is a rough approximation of mean sea level. The way that these rocks cement is that in the beach area, the thing that generally triggers the cementation process is the mixing of salt water and fresh water. So fresh water percolates through beaches, through dunes and beaches, and meets the sea water along sort of the intertidal zone. Often those little sediment gullies that you see on a beach, that's fresh water coming down towards base level. And where those meet, if the conditions are absolutely favorable for sort of precipitating a calcium carbonate cement or making a cement, then it can form. And usually in that environment, it's aragonite or micrite, which is a form of calcite that has sort of high magnesium and these needle types of structures. But the pH, sea surface temperature, atmospheric conditions, all of these things need to be pretty favorable to allow the cementation process to happen. In South Africa at the moment, that does not seem to be happening on the Cape South Coast or the Cape Coast at all. And the only place we've seen evidence of that happening now is in the more subtropical areas, for example, around Durban. And specifically on the Durban Bluff, I've mapped some beach rocks that contain whale harpoon heads and unexploded grenades and things from the Second World War, which indicate that that's less than 100 years old. The cementation of beach rock, studies around the world have shown that it can happen extremely quickly, whereas the cementation of dunes seems to be much slower. So the cementation in the dune environment, the type of diagenesis that takes place, it involves just rainwater percolating through the pores and precipitating calcite spar by the dissolution of the shell fragments in the dunes. So there's different types of cements that can be identified in these cemented rocks as well that can tell you in which part of the beach profile, roughly, they've been lithified. And oftentimes you have repeated cementation events within the pores, and that's linked to something that's already been cemented, and sea level fluctuates. There's an overprinting cement. We can identify things like that in thin sections. Along the Cape South Coast, it seems to me that the cementation process has stopped approximately 60,000 years ago, because most of the rocks that have been dated so far are not younger than that. So generally from 60,000 to 440,000 years is the time period of the record of quaternary cemented rocks that we're able to work with on the Cape South coast, both along the coast and offshore on the adjacent continental shelf, where we've sampled them by scuba diving for the most part, up to about 50 meters depth. I spoke a lot about sea level changes in the presentation yesterday, but I just want to say that, and earlier on, I just want to say that with sea level changes in the last 900,000 years since the mid-Pleistocene transition, when the current climates and glacial interglacial cycles that we know have been set in place, this sort of vertical level that we're dealing with is that sea levels have generally fluctuated from about 11 meters above present to 130 meters below present. So that's about 140 meter vertical range. And of course, depending on where you are along any parts of the coast, considering that the coastal plain and the continental shelf are two parts of one continuous feature, depending on the gradient of that plane or that slope, these vertical changes will have either negligible or profound effects on the coast at any given place. So if there's a low gradient and a shallow slope, a small vertical change will translate to a very big horizontal change. Whereas if it's a steep part of the coast, these changes don't have such a profound influence on how much landscape is lost or reclaimed with moving sea levels. So I'll start with the archaeology. So the Kelders Cave sequences have got records that approximately date from about 125,000 to about 60,000 years. Following 60,000 years, it's possible that maybe a dune has blocked off the cave or people stopped occupying the cave. And people, of course, shifted on the landscape, especially according to changes in sea level in this area. We've had a profound coastal adaptation on the Cape South coast that's seen in the archaeological records, at Pinnacle Point in particular, going back 170,000 years. So the progenitor population of Homo sapiens, according to the genetic records, may go back as far as about 200,000 years. So far, the oldest evidence on Earth for Homo sapiens is actually on the Cape South coast at the Pinnacle Point site, which goes back to 170,000 years. I've said that many times. But at about 160,000 years ago, there was quite a harsh glaciation in marine isotope stage 6. And in South Africa, this doesn't mean that we would have been covered in ice. Maybe only in the Lesotho Highlands, there might have been some glaciers or glacial activity. But generally, the impact would have been a dropping of sea level by about 130 meters, exposure of the continental shelf as a landscape, and certainly a different climate regime that came with that. So with things being a little bit more difficult for early populations of people and hunter-gatherers, it's believed by a lot of paleoanthropologists and archaeologists that the environment of the Cape South coast in some way allowed the survival of our species. So for instance, the ability to harvest shorelines for shellfish, such as Donaxera, which are white sand mussels, or Perna, which are black sand mussels, or brown mussels, sorry, Olycrickle, limpets. There's a really rich, protein-rich supply of food out there, coupled with exploitation of the fynbos and its carbohydrates, bulbs, and things that grow below the ground. It's believed that this enabled us to get through this very harsh glacial period and then to, of course, proliferate and spread across the globe following on from that. So people have studied, some of my colleagues have studied these different aspects of the ecosystem that could have been at the time, looking at the bulbs, looking at the fynbos, looking at the carbohydrate values, looking at calorific values of shellfish and of bulbs and of various different things, and compared that to other hunter-gatherer societies and even people living right now, such as in the Amazon. There's some really interesting work that's been done on this. And it basically points towards that this marine ecosystem, coupled with the very unique fynbos, coupled with an expanded plains landscape, which you would have when you drop sea level quite significantly, and the types of fauna that would have migrated across that plains landscape. All of these things probably gave a pretty fortuitous opportunity to survive a very difficult time in our early history. So the caves, the Kelders Caves, have been excavated since about the early 70s by Frank Schweitzer and Tony Tankard to contextualize these deposits that were coming out. Way back then, people already understood the sort of, or they, way back then, people grasped this idea of comings and goings of people, obviously being linked to environmental fluctuations, such as fluctuations in sea level. And of course, over the decades, better research on, or better ability to date the sea level changes and the sense and magnitude of these changes has enabled this coupling to be better described and better constrained. The caves were subsequently, they were re-excavated by Graham Avery, Richard Klein, Fred Grine, sort of in the time period leading up to about the 90s, then Curtis Marion in the late 90s as well. So the Kelders records have been readdressed several times. And I think it would actually be really interesting for the society to maybe get some of these archaeologists out to give a really detailed overview of the deposits that are now sandbagged up and have a walkway running over them for people to appreciate. So quite broadly, the coastline adjacent to the Kelders Cave is often dominated by hard rocks, so the Cape Fold Belt extending out onto the seafloor, which is quite unique in the context of the Cape seafloor. And the shelf itself is quite narrow compared to around the corner on the Agulhas Bank, which is a much wider shelf and a much lower gradient with a totally different lithology. Over here, the last glacial maximum shoreline, which is generally the shoreline at the times of most of these harsh glacials, is about 40 kilometers away from the present coast. So if you imagine 130 meters lower sea level being positioned about 40 kilometers away, that would be the situation in marine isotope stage 2, which is the last glacial maximum at about 20,000 years ago, and at marine isotope stage 6, which is the harsh glaciation that almost possibly wiped out our species, which was about 160,000 years ago. And in between, sea level takes a very long time to fall from the period of warming down to a glacial maximum, and it's really quick for it to rise after that. And that's just got to do with both orbital parameters, but also the sort of energy required to either build ice sheets or to destroy them. And you'll see if you look at sea level curves that it takes about 80,000 years to go from a peak interglacial to a peak glacial, but only about 20,000 years to get out of that glacial again and back into the next interglacial. Out there on the continental shelf, offshore of Walker Bay and around the Overberg area in general, the inner shelf and out to the mid shelf is a rocky area dominated by these sort of hard quartzite rocks, some interbedded shales, probably caves that would have formed at different elevations, thin acidic soils that would support things like certain types of fynbos. But below a depth of about 75 meters, which is probably about 25 kilometers out to sea approximately, once sea level drops below that elevation, it opens up a bit of a plains landscape, probably supporting grasslands, totally different kind of substrates, and much more like the substrates around the corner on the Paleo-Agulhas Plain or the Agulhas Bank. In that case, one would expect grasslands and the animals that come with that sort of migratory, possibly ecosystem. So the environmental changes can both be measured according to the cave stratigraphy, so looking at the changes in chemistry through the layers, looking at the types of resources that are being exploited, looking at the occupation intensity by people, looking at the stone tool technologies, various proxies from inside those records themselves, and then also compared to broader scale landscape types of proxy data. So looking at geological evidence of sea level change, looking at reconstructing these, the structural elements of these ancient landscapes. And we call them paleoscapes. So the paleoscape to us would describe a now extinct ecosystem. And it's a complete ecosystem that includes all elements of that. So right from the outset of trying to unravel a paleoscape. We tackle the geology and geophysics, climate, environment, pollens, evidence of what people were consuming, the stone tools that were being chosen to make certain tools within the different technologies that prevailed through the different time periods, how the changing environment might have impacted cognitive ability or necessity to innovate, and how people made these stone tools and what they would have used to do that. What wood they would have used to burn to heat treat silkweed, for instance. So it's a super complex system. It's a complete ecosystem, and it's now extinct, the one that has gone by in the past. And at any time slice, if you wish to reconstruct that, you've got to consider all of these aspects of the ecosystem within one sort of paleoscape package. And yeah, that's exactly the sort of work that we've been doing. And it's really fun to be able to walk people through some of these specific time slices going back to those periods, and using science and a bit of imagination to kind of put ourselves back into the shoes of the people that occupied that landscape before we did.
And are the soils in the caves particularly fossil rich?
Yeah, so the strata within the Kelders Caves definitely contain fauna, so bones from animals that have been consumed by people, or bones from animals that occupied the cave when people had left the cave, probably during times of glacials when people would have possibly been living on the continental shelf or in some sort of adjacent areas. So people would have exploited whatever was within a sort of general foraging radius for hunter-gatherers. And often these exploitations and the bones that are left behind can tell us about what sort of environment might have been there, given that these animals have been supported within it. We're also quite lucky on the Cape South coast that a lot of the Aeolianites preserve these beautiful trackways or trace fossils of animals and people that were moving across these coastal dunes before they were lithified into rocks. So by comparing faunal assemblages from archaeological sites to trackways left behind of things that don't always end up in archaeological sites, we're able to gain a much clearer idea of the sort of the distribution of animals within the environment of these paleoscapes. So for instance, there are giraffe trackways near Stilbaai, but people wouldn't have necessarily brought giraffe bones back into a cave. So it wasn't known that they were on that landscape until their footprints were discovered. And the presence of giraffes would indicate a need for some sort of savanna vegetation, and constructing the geophysics plus these trackways showed these wide sort of floodplains which probably supported riparian vegetation, and everything kind of comes together to build these broader pictures that we're trying to do.
Hayley, can I please backtrack on one issue? Why is it so difficult to date the conglomerate overlay? Is it because the rocks simply have not been dated, or are there some other complications?
So firstly, dating methods are constantly being improved and worked on. That's one aspect of geoscience, the geochronology, that's really burgeoned in the last 20 or 30 years or so. It still, though, remains very difficult to date rocks that come from the Neogene or the Paleogene, so between the Mesozoic and the present. Unless, of course, if there was volcanic activity, then you've got a lot of opportunity to get radiometric dates. But if they're sedimentary rocks and if they do not contain fossils that are diagnostic fossils, it's really difficult to just date those sediments. And in a lot of cases, it just simply doesn't really work to use strontium curves, or the few options that are there don't necessarily always work on a specific deposit. When the rocks are younger than about 500,000 years, for the most part, the method that's used most commonly is optically stimulated luminescence, which essentially extracts a particle of sand from the center of this rock that has not been exposed to sunlight since it was lying on an open beach or an open dune and was then buried. So imagine a particle of sand exposed on a beach or dune. It becomes buried, it becomes compacted, it turns into a rock. We can drill a little core into one of these rocks, and in a very sort of dark environment, in a lab that does luminescence dating, they can calculate the the time that this particle has not been exposed to raw sunlight, and this is luminescence dating. And it's a really useful technique, especially here in South Africa, where we have obviously enough of a luminescence signal for it to work well. And we have these deposits of beach and dune material that allow for that. It's the same method that's often used to date the layers within the stratigraphy of the cave sites as well. So in the case of our work on the Cape South Coast, we've had the same dating lab at the University of Wollongong, led by Zenobia Jacobs, who's dated the cave stratigraphy and the dune and beach deposits out on the landscape. So we have a really good opportunity to benchmark these ages. We're also really fortunate on the Cape South Coast. Very bizarrely, when Mount Toba erupted, a supervolcano that erupted 74,000 years ago, it spewed tephra all over the world. And these Toba tephra particles are also preserved in the cave stratigraphies around our Middle Stone Age deposits. And these can get a really precise age. So the Toba tephra at Pinnacle Point allowed a real good benchmark to test the OSL against and the reliability of the method. And in fact, it showed that the method has been giving very good results, pretty reliable results. So whenever there's a chance to sort of bring in alternate methods to test against anything that you're using, that's a really good thing to be able to do. So, but when you date things that are older than about 300,000 years or so, then the geochronologists that do luminescence dating have to use a system called TT-OSL, thermally transferred optically stimulated luminescence, so TT-OSL. So they can use TT-OSL that allows this sort of clock to be set further back. So they can date things that come from marine isotope stage 11. But the issue with conglomerates is often that you need a really good amount of matrix material to use TT-OSL to get a reliable date on that unit. It's quite expensive, and of course it's quite difficult for the geochronologists to do, so it hasn't been done everywhere. But if that, for example, were to be tested on these conglomerates at Kelders, and it turns out that they're older than what the method can produce, then they probably would be de Hoopvlee age.
Haley, thank you very much. I think I've exploited you more than enough now. You've given us such a fantastic overview. Thank you also for spending the time with us at the caves on site and all the information you've given us. And thank you for being so generous with your knowledge. All the best for your future studies. And thank you for visiting us. I hope you'll do so again. Goodbye.